you. Hello, I am Alex Richardson, and today I'll be presenting on my summer work on improving the search results for a medical studies database. The title of my presentation is Concept Hierarchy Development using UMLS for PhenDisco. My mentor for this assignment was Hyoni Kim. I am currently a student at UCSD pursuing a Bachelor of Science in Computer Science with a specialization in bioinformatics. So a little background information. PhenDisco is a search platform currently being developed at the UCSD Division of Biomedical Informatics. Its purpose is to improve search results for the database of genotypes and phenotypes through concept-based search. The database of genotypes and phenotypes is an archive containing studies on the interaction between genotypes and phenotypes, and the variables of these studies are standardized in a separate process called PFinder for use with PhenDisco. PhenDisco currently only supports synonym expansion, but we are currently in the process of implementing hierarchy expansion functionality. So as you can see to the right of the search bar, the PhenDisco currently does support concept-based search, except currently this is limited to synonym expansion. So for example, if a researcher wanted to find studies related to heart disease, it currently would expand the search to include results for cardiac disease as well as cardiac disorder. We would like to improve the search results to also include medically related terms such as pericarditis or myocardial infarction with this to help to further aid the researchers. So our goal is to implement this hierarchy-based expansion of the searching. To do this, though, we first needed to develop a hierarchy for the expansion. So we decided to use the UMLS and to create a subset hierarchy from it. This is just an example of the current hierarchy we have in progress. It needs a bit of cleaning up, but it gives you an idea of the behind the scenes of the hierarchy expansion. So the UMLS is a unified medical language system. It's a compilation of more than 100 medical terminology vocabularies, and it also contains the relationships between these medical terms. I use the relationships for harvesting the algorithm, for harvesting relationships to build the hierarchy. So the three algorithms that I've developed, first is relationship harvesting, followed by node legitimacy testing, and finally redundancy elimination. So to begin building hierarchy, we first have to harvest all the relationships related to the input GUIs from the UMLS database. So we first begin, the red ovals represent the input GUIs we start with. We would query their parents from the UMLS database and save these relationships. The parents then become the children, and we would query their parents. We query their parents and save these relationships as well. The process continues until we reach a specified top hierarchy concept or until we reach the top of the UMLS database. So now we will have a hierarchy implied by the relationships we have gathered, except it also contains a lot of excess information and redundant relationships that need to be cleaned up. To begin the cleanup process, we use node legitimacy testing. So there are some nodes or input GUIs who have no natural relationships to a top-tier concept, such as these. And then there are also nodes which do not follow. We have a policy that each node must have 2 or more children, and these nodes must also be removed. But as you can see, one of them is an input GUI, which must be in the final hierarchy, so it is still considered valid. So to start, we first remove, for the nodes that don't reach up to a top-tier hierarchy, we simply group them into a miscellaneous category to be later hand-mapped out by a medical professional. And then for the nodes with less than 2 children, we simply create a direct relationship between its child and its parent. Now we need to reduce the redundancy of relationships. A relationship is considered redundant when a child has both a direct and an indirect relationship to a parent. These relationships must be eliminated to improve the search results. And then after this occurs, some nodes will now have less than 2 children and violate the 2-child policy, so node legitimacy testing must once again be performed. The current status, we are currently still optimizing the cleanup process, specifically the node redundancy elimination. we are using a training set of 50 cardiovascular disease concepts to develop the algorithm. These are chosen because they are fairly straightforward and they have possibility to build a hierarchy out of. Some of the challenges we face, there are many inherent problems with the UMLS database itself, which is one of the reasons we use a subset of it. There are concept hierarchy loops, such as venous thrombosis is a child of thrombosis, which is a child of vascular disease, but for some reason vascular diseases is a child of venous thrombosis again, which causes problems with the algorithm. There's also concept islands within the UMLS database in which these concepts have no parents, so they are simply added to the miscellaneous category to be hand mapped out later. Redundant relationships are the current issue at hand we are trying to clean up, and then we will need to test the robustness and scalability of this approach to the actual database of genotypes and phenotypes. So in summary, I've been working this summer on improving the concept-based search of the PhenDisco search browser for the database of genotypes and phenotypes. Currently, we are implementing the hierarchy-based expansion for the search results, and we are still in the process of the cleaning up the algorithms for the redundancy elimination. For the future, we hopefully plan to soon apply this to the actual phenotypic variable concepts in the database of genotypes and phenotypes. So I would like to thank my mentor, Hyoni Kim, collaborators Emily Fireman and Edna Shenvi, as well as all professors, staff, and interns, iDASH, DBMI, NHLBI, and the National Institute of Health. I will now take any questions. We actually use a hybrid method in which our collaborator Edna Shenvi creates top-down hierarchies, which my algorithm builds up to.